So all of you have inputted the data. Now, what is the problem in this data? There is large number of. So if you look at the data which is there, we have 7,352 rows and 563. This is a classification problem. If this is a classification problem, what was the rule? For classification, the minimum sample size is 50 observations per variable. You should have minimum 50 rows or 50 observations. Now, if you multiply 563 into 50, you will get a value of 28,150. So since this is a classification problem and the minimum sample size required for the classification problem is 50 observations per variable, we need to have 28,150 rows. But how many rows we actually had? 7,352. Now, when you have such situation, we call this as high dimensional is where too many variables, less number of high dimensional data is where we have too many but less number of rows or observations. Now, when you have such type of data, we need to use dimensionality reduction algorithms. Dimensionality reduction algorithms must be used that reduce the dimensionality or the number of variables not by deleting, combining them, also retain high dimensionality is a problem when you have less number of rows and more number of variables. We cannot run until we correct the dimensionality. Dimensionality means we need to reduce the number of. Now, dimensionality reduction algorithms do not reduce the variables by deleting. They don't delete the variables. Rather, they combine the variables. How do they combine? Combining based on similarity using either correlation matrix or covariance matrix will be used for combining the data. Now, within dimensionality reduction, the most used algorithm is principle, also called as PCA. It is a very popular dimensionality reduction algorithm which is widely used in industry. Principal component analysis. PCA is an unsupervised learning algorithm. That converts observations correlated through orthogonal transformation to orthogonal transformation. The newly transformed are called as principal components. The newly combined or transformed features are called as principal components. What PC algorithm will do is, first we'll create a covariance matrix, and taking that covariance matrix as an input and using orthogonal transformation, it converts the variables into transformed features called principal components. After this process, we no longer call them as variables. We will call them as components, because each component is a combination of variables. So we use the word components. They will be no longer called as variables. They will be called as. Now you might get the doubt, what is orthogonal? Orthogonal is uncorrelated correlation. Orthogonal is uncorrelated set of features whose correlation will be, and two important components are important. Two important things are very important calculation is the eigenvectors and eigenvalues. If there is a square matrix M, and a non-zero vector, V will be eigenvector of A will be eigenvector if scalar multiple. So AV is equal to lambda V. V is the eigenvector, lambda is the eigen. Or if you still want the formulas, calculated formulas, use this one, eigenvalue. The eigenvalue equation is, here V and X are same. Ax minus lambda X is equal to 0. A minus lambda I into X is equal to 0, where I is the identity matrix. So eigenvalue and eigen equation, this is the ones which you are going to use to transform the data. Standardization or normalization must be done. The input of PCA will either be correlation matrix or covariance matrix.
Sir, can you take it a bit up?
Now the PCA algorithm uses this calculation. So these are the steps that are involved in calculating, doing the PCA or principal component analysis. Now all of you open the Excel sheet which I have already forwarded to you. Now calculate the mean of each row. So there are 6 variables. We are going to convert them, there are 6 variables, reduce them to 2 from each row observation. So is equal to 2 minus 4.5. We will fix the 4.5 because it is constant. The mean has to be fixed by pressing Fn plus F4. The mean has to be fixed by pressing Fn and F4. So as per the algorithm steps, we have centered the data by subtracting the mean from each variable. Now we have to calculate the covariance matrix. Now we have to calculate the covariance. So data tab, data analysis, input range, labels in first row, output range. Oh, we have to calculate the covariance of the rows only, not the variables. This is a larger matrix. Select the values, group by rows. Select these values, only the values. Don't select the headers. Select the values. Do not select the headers. Grouped by click on rows. And output range, select some empty cells. Select only the numbers. Do not select the column headers. Group by rows. Output range, select some empty cells below and click OK. You will get the covariance matrix. Grouped by has to be rows, not columns. Default will be columns. Grouped by is rows. So we got the covariance matrix. So the covariance matrix is, let us round it off, 2.92, 3.67, 3.67. I just put them into rounded off format. The covariance matrix is this rounded off. Lambda is an eigenvalue for a matrix M if this characteristic equation is met. The characteristic equation is determinant of M minus is equal to 0, where I is the identity. Determinant of M minus lambda I is equal to 0, where I is the identity matrix. So lambda into I would be what? Lambda, right? Here identity matrix is 1, 0, 0, 1. Here the identity matrix is 1, 0, 0, 1. Identity matrix is where diagonals are ones. Rest of all elements are. Now if you multiply lambda with identity matrix, you will get lambda 0, 0, lambda. Lambda 0 and lambda 0. Here identity matrix is 1, 0, 0, 1. So I multiplied lambda with I. We get lambda 0 and 0. This is right, lambda I. Matrix minus lambda I is equal to 0. Now let us create the quadratic equation. Multiply both the matrices. 2.92 minus lambda, 67 minus lambda, 3.67 into 3.67 is equal to row column. You multiply row with matrix multiplication. So if you if you solve this equation, lambda square minus 8.59 plus 3.09 is equal to lambda square minus 8.59 lambda plus 3.09 is equal to, so what is this? This is a quadratic. Lambda square minus 8.59 lambda plus 3.09 is equal to 0. Once you solve the quadratic equation, you will get the lambda values as 8.22 and 0. Now eigenvector is equal to m into x is equal to lambda into x. M into x is equal to lambda into m is covariance matrix, x is the eigen and lambda eigen value. So eigenvector m into x is equal to lambda into x, where m is the covariance matrix, x is the eigenvector, and lambda is the eigenvalue. So we already know our covariance matrix, right? This is our covariance matrix. Let us assume x as x1 and x2. Assume x is x1 and x2. We need to find the values of x. This is equal to, we will take the larger eigenvalue 8.22 and x1 and x2. The lambda value we will take it as 8.22. That is the larger lambda value, right? We will take the larger lambda value. This is the equation, right? Mx into is equal to lambda into x. Mx is equal to lambda into x. Now, if you multiply these two equations, the first equation would be 2.92 into x1 plus 3.67 into x2 is equal to 8.22 into x1. The second equation would be 3.67 into x1, 67 into x2 is equal to 8.22 into x2. Now, if you further solve this equation, this will become 5.3 x1 is equal to 3.67 x2. This will become 3.67 is equal to 2.55 x2. How did you get 5.3 x1? 8.22 x1 minus 2.9 x1. Here 8.22 x2 minus 5.67 x2. So we can say from this output, x1 is equal to 69 x2. x1 is equal to 0.69 component 1 or our eigenvector. First we will say our eigenvector is equal to x1 is 2.55, x2 is, so if you want to check 2.55 into 0.x2, right, is equal to 0.69 multiplied by 3.67. You get somewhere around 2.55, rounded off, is 2.55, comp 2 is 3. So we have converted 6 variables into 2 components. We have converted 6 variables into 2 components using covariance and eigenvalues and eigenvector calculation. So this is the process which is followed by the algorithm principal component analysis to convert or reduce the data. Did we delete any data here? We have not deleted any data. But we have used a covariance matrix, and based on that covariance matrix, determinant of m minus lambda I is equal to 0. That will give us our eigenvalues. Then mx is equal to lambda x will give us our eigenvectors. Eigenvectors are nothing but your principal components. So finally, the 6 variables reduced to 2 variables, component 1 and component. They will no longer be called as variables. They will be called as, right? Because they are combination of. So this is the procedure which is followed by principal component analysis to reduce. Nowadays, even very complex algorithm has been developed to work on large scale data. Even very complex algorithm has been developed to work on large scale data or big data, we call it as singular value decomposition. Singular value decomposition is the one which is being used right now these days within the PCA also. Within PCA also, we use this SVD algorithm for reducing. This is considered to be faster than the PCA. PCA itself is faster, but SVD is considered even faster than, eigenvalues and eigenvectors. So you can run PCA with eigenvalues and eigenvectors, or you can also run it with, trying to get an easy one which you will understand. This is eigenvalue decomposition. Singular value decomposition. A is equal to S sigma ut. S is the eigenvectors of A transpose of A. Sigma is the diagonal matrix of singular values of A transpose of A. And U transpose is eigenvectors of A into A transpose. So this is a slightly complex calculation, but this is considered to be slightly faster, slightly better than eigenvalues and eigenvectors. It also uses the same eigenvalues and eigenvectors. It uses the same eigenvalue, eigenvector calculation proposed to work on large scale data. Netflix uses it in recommender systems. Amazon uses it in recommendation systems and recommender engines. So this is the process of calculating the eigenvalues and eigenvectors for a simple calculation which I can show you on. So summarizing PCA in a nutshell, the data will first take, finally it starts with the computation of covariance. matrix. From covariance matrix, we will calculate eigenvectors plus eigenvalues. So eigen EAG of covariance of data, the eigenvalues and eigenvectors, you will pick the highest eigenvalue. You will pick the highest and then you will project it onto the data points. So it all starts with computation of covariance matrix. All right, got this? So this is the process of eigenvalues and eigenvectors, which transform your data from large dimension to smaller dimension. The biggest, yeah. No, we have to decide. That is what I'm going to discuss now. How to decide the number of components in PCA. Like K means we have to decide K value. In KNN, we have to decide K value. In K means we look at the elbow plot and we also look at the Silhouette score and we will come out of it. And in K neighbors also we look at the variance where it is becoming stagnating. Similarly, for selecting the best number of principal components, we don't have a fixed formula. We have to randomly start with some basic component, with some component number, and then we will plot the variance or the change that is happening in the components or variability in the components into a line plot, and we look for the stagnation. How to decide if n components is a critical challenge. So here one method. Suppose you want the variance to be constant at 85% or you want the variance to be below 95%. You have to give the n components in decimal format. If you want an exact amount of variance to be kept in data, after applying PCA, you have to specify a float between 0 and 1 to the hyperparameter tuning. How to decide n underscore components? The first method is, if you want to have a specific amount of in your data, then you have to specify a float between 0.0 to 1. 85% variance, 90% variance, or 95% variance. Typically, we look at 90% as our variance as a general purpose. So this is one method of selecting the number of. So the algorithm will automatically select the best number of that gives 85%. If you use this methodology, it automatically selects the components that gives the 85% variance in your data. The second method, plot the explained variance percentage of individual total variance captured by all components. The second method which we generally use is, you can create a plot of total variance captured by the cumulative variance. We will calculate the cumulative variance. So what we will do here is, the components, the number of components capture almost all the variance in the data that needs to be selected. N underscore components that capture almost all the variance in the data. This method we generally use in R, because this code is not available in Python. It is available in R. That is what he is also saying. In fact, extra library, we get this model like this. Component 1 is explaining 44.3 variance. Component 2, 19%. And from here onwards, it is very, very marginal. So what we will do, we will select how many, the number of variance that explain the 90% of this thing. I think by component 5, we have all the variance. So scree plot, you remember, scree plot is there, like how we do in K means, na, where the bend, elbow bend happens, na? The point at which the elbow bend happens will be our number of components, scree plot. Then we also have something called, so in this plot, it is happening at 1 only. That means only 2 components. So see, the bend is happening at 1 only. That means only 2 components, component 0 and component 10 variables or 6 variables are been converted into 2 components. So Kaiser rule says it is recommended to keep all the components with eigenvalues greater than all the eigenvalues greater than 1, the components will be retained. So these are different methods which are used for finding the one, but we will be using the script, what you call the method where we plot the variance, and then we will see where the thing is, what you call explained variance is, stagnating. Sorry, I should have kept it article because it has all the. So we will try to implement these methods and find out which is the best method for finding out the n components. So let's take a break and then come back and implement it in Python. Online guys, please take your break and we'll meet after 15 minutes. So that activity trained data, what we are seeing here is data collected through a mobile phone sensors. Mobile phone has sensors, accelerometer, pedometer, lot of sensors will be there in your mobile phone. Typically, any phone about 10,000 rupees, you will have these sensors in the phone. Accelerometer will study the body position. Pedometer will study the number of steps you are taking or whether you're running, and all those sensors are there. Na? So this is the data captured through those sensors in a mobile phone. Now, these are the values which have already been standardized. If you see the values, you can see, right? They have already been, okay. So already the data is scaled. They have given us the scaled data, which is collected by the different sensors from a mobile phone. I think there are 6 subjects or 6 people who gave this data. And the activity is the dependent variable. The activity variable, you can see on the right side, you see the activity variable, right? Standing and all, these are the dependent variable. So if you look at activity train dot activity dot value counts, you can see there are 6 activities which are there in our data. There are 6 activities which are there in our data: laying, standing, sitting, walking upstairs, walking downstairs. There are 6 activities which are being tracked or measured using the various sensors in your mobile phone. Now, let us start the pre-processing. Label encoder has to be run, right? Activity train is equal to activity train dot drop single quote. We'll drop the subject, which is an ID, comma, axis is equal to 1. Y is equal to activity train, activity, X is equal to activity train dot drop activity, comma, axis is equal to 1. We have split the data into dependent variable and independent variable. From sklearn dot pre-processing, import label encoder. Y is equal to label encoder dot fit underscore y dot. See, it has converted them into. Now we will implement the method of float. We will implement the float method. Do scaling. Can you do scaling on? Can you do scaling on categorical data? But label encoding is categorical. No? It identifies into categories. sklearn dot decomposition PCA. So typically 95% to 99%. So typically it is expected that the explained variance to be between 95% and 99%. PCA underscore 95 is equal to PCA n underscore components 0. PCA underscore 95 underscore, or let us say dot fit. So 67 components. If you take 95%, it is reducing it to 67 components. If you want explained variance to be 95%, 67 components, it is reducing. So X underscore PCA underscore 95 is equal to PCA underscore 95 dot transform of X. So X underscore dot, it has reduced the variables to 67 components from 563 to this is 95% explained variance. 99%. Implement the same process for 99% explained variance and see how many components you will get. 155. If it is 99% explained variance, 155. That means as the explained variance increases, you will get high. So how many you got? 155 into 50. Oh, it will be slightly higher, right? 7,500 something will come. Yeah, how to select multiple cells in Jupyter Notebook? Control shift, but that is not working. No? Command shift, but it's not working. Shift down or up to select multiple cells. Why shift thing is not working? Acha. First you have to press escape key, command mode, then shift up or down. But escape key, when I press it, it is not turning into blue. Control C. Oh, everything is getting placed in one cell only. Huh? Okay, I think I have to do escape key and then control V. Escape key and control V. So 99, 99, 99, 99, 99. So 199% is giving you 155, but again it is giving us more number of. So we can select some value between 95% and 98%. So 95 and 99%. 2 types of thing we have done. Now let us do the scree plot thing. So let us say PCA underscore scree is equal to n underscore components 280. 563 is there, na? I'm randomly choosing 280, right? I'm just doing, which is 560 by some value I have given, right? To plot the scree plot and then we can get it. PCA underscore scree underscore explained variance. Explained variance is equal to NP dot, because variance is a very large number, na? E plus 0 something you will get. NP dot round PCA scree dot PCA scree dot fit. We have not fit the model X. I will do it today. Explained variance PLT dot plot PCA underscore scree explained var comma marker is equal to PLT dot X label PLT dot Y label PLT dot show. We should not have done the cumulative sum. Explained variance. I think after 50 only it is becoming very stagnant, right? PLT dot xlim 0 comma 50. So this is giving us even more smaller eigenvalues in somewhere here. So this is not giving us a good one. With the explained variance scree plot, we are not able to get proper identification, right? So scree plot is not giving us any chance here. So let's move ahead. All of you done with this? We will be using cumulative underscore variance underscore ratio to find the x underscore is equal to NP dot cumulative sum NP dot round x underscore PCA dot scree dot explained ratio comma 4 into 100. PLT dot is equal to 30 comma 10 with comma AX is equal to PLT dot XE is equal to NP dot arrange 0 comma 250 step is equal to Y is equal to X underscore PCA. PLT dot plot, PLT dot 0 comma 1.1 PLT dot plot xi comma is equal to 280 here, but I've shaped 12 comma 280 here. Okay, we will do the normal plotting. So we have plotted the components and the variance. PLT dot AX H line underscore PCA is equal to 0.95. PLT dot AX line Y is equal to 95. Color is equal to red. So you can see the 95% line, which is cutting around. I think 67 is the right one, right? 67 is what we are getting for 95. If it is 99, we get the same thing, 155, right? So you can use this method, cumulative variance with 95 variance. 67 is the cutoff point. So this is giving us the cutoff point. 67 components we can take. So 95% threshold. 65%, 67 means it's okay, right? Or we can take up to 116 components, 98%. So we'll take 98%, 116 components. Somewhere between 95 to 99 we have to take. Typically that is what we look at, 95 to 95%, 95 to 99. Already process చేస్తున్నారమ్మా, లేదు already process చేస్తున్నారు, ఇప్పుడే అవుతుంది. So build the model with n components 116. Build a final model with n components 116. First fit the model, then transform the model with components of 116. So the final model, we will set it with 116 components, right? X underscore PCA underscore final. All right, build logistic regression on this data, logistic regression. So X underscore PC underscore final is the X. Generally we do X comma Y, right? Dot fit. Here it is X underscore PC underscore final. In the dot fit, it is X underscore PC underscore final comma Y. Build all models. Find the best fit model. sklearn dot linear underscore model logistic regression. Logit is equal to logistic multi underscore class is equal to multinomial. Logit model is equal to logit dot fit X underscore PC underscore final comma Y. But why I didn't get output? No, it is correct only. Given it as PCA final. Why I didn't get the output? Okay, here let me check, because I thought I have cleared all. Because the report which was sent to me, there was only one pending, which I have cleared. I will do that here. Print classification report, Y comma logit predict. 98% accuracy, right? Logistic regression itself is a good model for this data. Is it overfitting? And P dot mean Model selection, I think it's a good fit model. 92.60. It's a good fit model. Cross-val score is also 92.60, which is a good fit model. Build other models, decision tree classifier, random forest classifier, gradient boosting classifier, multinomial neighbors.
ఇప్పుడు వరుస 7 minutes Saturday, Sunday, and how many hundred from CSC getting there is an అట్టే ఉండమనబ్బా ఇద్దరు నీకు పైసలు ఎందుకు వేస్ట్ ఆటే చూడని ఇంకా పోషిస్తాడు అంటే సైన్ ఇవ్వడానికి పోతున్నా అంటాడు అంటే సైన్ పెట్టని పోతున్నా అని అని आपको वो मैं विद्यार्थी के बारे में बात कर like other than you people in your class who are in CSC or writing lab what's the only one we are तो बिहार के कौन हाँ ये तो जितना आटे बोलता रहा बहुत कितना हाँ that is an internship opportunity for CSC तो पांडे internship hello निकल आ सकता है ये बस CSC उतना पब्लिश कितना लिखा देगा whatever पब्लिश अच्छा हैप्पी बर्थडे मैं 20 का लाइक दूंगा లేదు బాబా బస్సు ఆపేస్తారు కదా మరి ప్లేస్ ఐడియా నువ్వు ఒక సాయంత్రం మాట్లాడుతున్నాం
Next class will start with time series. Time series is Python. Related time series. Ready?